No matter how hard you might try, you probably can't see through this prism. Move over, H.G. Wells, Harry Potter, Susan Storm. Invisibility isn't just for fiction anymore. In fact, if you have a 3D printer, you might just be able to make something vanish before your eyes. Well, sort of. Scientists at Duke University have been working on developing an invisibility cloak, and they have succeeded to a degree. The cloak works by bending a certain wave of light. To learn more, if we can find him, we've brought in Yaroslav Urzhumov. He's an assistant research professor and the technical coordinator of the Center for Metamaterials and Integrated Plasmonics at Duke University. Welcome, Yaroslav.
Hi.
From our earliest imaginings, man's wanted to do two things. He's wanted to be able to fly and become invisible. Well, we've clearly taken care of the flying part. Tell me how you're approaching the vanishing act.
So once you start talking about invisibility, the important thing to understand first is what is invisibility. And you can't understand what it is without understanding first what visibility is. So in other words, you got to ask the question how we see things, why we see them, and most importantly, who is the observer who is seeing those things? And so the answer actually depends on the situation and the context of visibility you're talking about. So let me expand on this so that you can better understand why we call this invisibility cloak. When a pilot is driving or riding an airplane, I should say, they can use their eyes to see the surroundings. However, when they are flying through a dense cloud, they can see nothing. In that case, their vision becomes a microwave radar. That's the only means they have to see other things because optical wavelength of light is just too short compared to the size of the water droplets in the atmosphere. So that's why the cloud is not transparent. So what is an invisibility device in our definition? An invisibility device should be able to make an object that is normally visible, invisible in the same context, in the same situation.
So when you say invisible, this type of invisibility is somewhat similar to the way a stealth bomber may be invisible to radar?
That is correct. That's exactly what I have in mind. If you envision a small aircraft flying way, way high in the stratosphere, you cannot see it from Earth with your naked eyes. You can see it with a radar, and that's the only means you have to see it. So now if this aircraft is now invisible to microwaves, then all of a sudden we have no means to sense its presence. So yes, indeed, stealth is a form of invisibility. However, it's actually more limited form of invisibility than the one we devised here.
This isn't your first stab at invisibility, or it's not even your first success. Tell me about what you've achieved and how this one is different.
So visible light is a form of electromagnetic radiation, and we see things by three different routes. We can either see reflections from the objects, we can see scattering from the objects, and finally we can see the silhouette of an object when it's between our eyes and a source of light, such as sun or moon or a lightning bulb or anything like that. So for the object to become completely invisible, a structure needs to completely eliminate all these three things. It needs to suppress reflection, it needs to eliminate scattering, and it needs to eliminate the shadow of an object, because that's how we see a silhouette. So what was done in terms of stealth development in the past for the aircraft is only one of those three things. It eliminates reflections from the surface of an aircraft coated with a special material. Now, you still have scattering, which is reflections in all kinds of directions other than the backwards direction. And you also still have the silhouette. So the conventional stealth technique is capable to defeat the so-called monostatic radar, which is the simplest form of radar. But it is not able to hide the same airplane from the so-called multistatic radars, which are basically arrays of radars which are able to send pulses in different directions and receive them from different directions. So our structure in addition to suppressing reflection and scattering in different directions, also eliminates the shadow of an object. So in our paper, we have experimental measurements of electromagnetic field distributions around a metal cylinder coated with the dielectric composite material, which comprises the cloak. And you can clearly see how a plane wave, which is essentially an electromagnetic beam of very large width, propagates around the structure, and it gets recreated in the shadow zone of the cylinder, the area that normally would have very low intensity of light because it is shadowed, the source is shadowed by this opaque object such as a metal cylinder. The cloak is capable to guide electromagnetic radiation around objects of essentially arbitrary shape. The new cloak that we are reporting recently is actually purely polymer-based. There's no metal involved. So the immediate advantage is that it's very cheap to fabricate by virtue of rapid prototyping. It's also very light, and it can be very mechanically stable, very rigid. The polymers that we use are called ABS, for acrylonitrile butadiene styrene, if you care. Those are very lightweight plastics that are only slightly heavier than water. There's no need to use expensive metals such as copper, gold, or other metals with very high conductivity, which was necessary in the previous technology.
It sounds like you're really close.
That's right. So we do think that once our results are inspected by the scientific community, someone will come up with the visible version of the cloak very soon, because like I said, nanotechnologies are out there. And if you want to cloak something maybe a dozen wavelengths in diameter, which amounts to several microns for visible light, it can be done in a couple of months. And I expect it to happen actually relatively soon, probably even this year.
Wow.
And the challenge in the future will be in trying to make those structures larger, achieve macroscopic visible wavelength cloaks. And also the other challenge is increasing the range of wavelengths.
Why did you decide to use a 3D printer? Was it giving you finer control?
Well, it's actually all about manual labor. Manual labor is the most expensive part. So if you look at the metallic cloaks that were fabricated previously, they were essentially handcrafted. So first you use photolithography and etching to create a pattern of very small metallic elements on a plastic substrate, very thin substrate. But then you have to cut pieces of that substrate and essentially hand weave them into these structures that look like grids of plastic elements with metallic elements printed on them. It is very labor intensive, and very few people are capable of both designing those structures and also building them manually. Now, with a push of a button, someone like me who has no extensive experience with nanofabrication or even lithography can fabricate those structures overnight. I think that's pretty exciting.
It's pretty cool. Now, you mentioned that you built this invisibility cloak using a cylinder and a pyramid. How shape-specific, how important is the shape in building this cloak?
Well, for the older cloak that was designed by our graduate student, Nathan Landy, the shape was very important. That technology was based on a very specific theory of cloaking called transformation optics. And in order to simplify the design, they had to use linear transformations. And those linear transformations basically necessitate that the boundaries of the cloak are straight. That's why the diamond shape, right? So it has flat facets. The technology that I use now, the methodology that I use now, is actually not constrained to the concepts of transformation optics. It's a more general shape optimization methodology. And so, in principle, if you are not happy with cylindrical shapes of the interior of the cloak, I can run this algorithm for any shape that you give me. You can give me, for example, a CAD file describing a soldier's helmet or a vehicle, any shape that you can come up with. And we can design a cloak that has very similar performance metrics with an arbitrary but predefined shape of the interior as well as exterior.
Now, I would imagine that if you're trying to work with invisibility, shape is one thing you would want to look at. Size is another, because if you do have many, many different pulses, many different wavelengths going after your object, the larger it is, the harder it is to disguise. Is size a limitation?
Well, so you got it correctly. You got to the bottom of this limitation of cloaking technology. There is a relationship between the size of the cloak and the range of frequencies within which it may work. So it's not like we cannot make these cloaks much larger, but as we do so, there's a price to pay, what they call bandwidth of these devices. Bandwidth is a range of frequencies within which it performs as desired. The bandwidth decreases as those structures are scaled up in size. Now, there is good news specifically with this novel development of mine. With this shape optimization approach, we discovered that it is possible to scale these structures up without simultaneously increasing the volume of the material involved. What I discovered through numerical calculations is that if you start with a cloak that is about one wavelength of electromagnetic radiation thick, whatever the size of the object in the interior you may want to have, it is possible to still design a structure only one wavelength thick. That is why we call them dielectric coatings, because if you imagine building this structure hiding a pillar or a small vehicle or a small building that is, let's say, several meters in size, and the cloak itself is only 3 centimeters, then, it's a very small relative mass added to the total mass of the system. It is very different from the cloaks that were previously proposed, such as this diamond-shaped cloak, which had only 50% of its volume hidden inside, and the rest is basically just added volume, added mass that serves no useful purpose other than conducting the waves around the object to be made invisible.
Clearly, making something invisible has a cool factor, whether it's to be Tom Sawyer and be able to hear what people are talking about you behind their backs, or whether it's to do something more noble. But what do you imagine to be the practical implications of invisibility? Is this primarily military? Are there civilian applications you're hunting for?
Well, actually, considering the innate limitations that come from the laws of physics, I honestly am not sure if there will be plenty of military applications for cloaking, at least within the scope of cloaking ideas that we have right now. I would say the developments that happened here at Duke recently have more civilian applications in microwave communications than they do in the military. However, of course, the military also do use microwave communications, so there's some overlap in the use there. Now, let me explain what I envision for this cloak as far as microwave communications are concerned. There's this well-known problem of antenna blockage, which is basically that if you have an object opaque to microwaves or whatever radio frequency waves the antenna emits, and this object is close enough to the antenna, it is basically blocking the view of the antenna. And when that antenna tries to communicate with another antenna, and this obstacle is blocking the line of sight between the two, you have a problem. Communication efficiency drops, and it may actually drop below an acceptable level, so the communication is completely cut off. And so in situations where you absolutely have to have that obstacle, you cannot remove it, you could just coat it with these polymer coatings made out of dielectric composites, we've discovered, and the microwaves will efficiently go kind of through the obstacle. So you don't have to do anything to the antenna itself. All you do is you coat the obstacle, assuming you do have control over it. So you might be able to have point-to-point communication through pillars, inside buildings, which, by the way, is a huge issue if you consider much higher frequency millimeter wave and terahertz communication technologies that are emerging. Millimeter waves are not able to diffract efficiently around obstacles that are larger than a centimeter or a few centimeters. So even relatively small obstacles are problems for extremely high-frequency communications. So in other words, in a crowded environment, when you have a lot of scattering and reflecting objects, but you do require microwave communication, reliable communication, you might be able to eliminate interference of all these opaque objects with the antennas.
So let's move from the world of the practical to the world of science fiction, or perhaps science fiction soon to become science reality. I understand that you think that progressing along this trail, you may be able to make an object which is actually invisible to the visual spectrum as well.
That is correct. Well, first of all, we know that theoretically the structures that we have designed can be scaled down in size such that the operational wavelength will fall into the visible spectrum. So technically that gives you an optical cloak that works with visible light. However, of course, as you scale it down, you also reduce the size of the cavity in which you can put your object to be made invisible. So in order for this to become interesting to humans, first you need to scale the cloak up, and then you need to scale it down so that it's invisible to the optical light. So let me explain what I mean by this up and down scaling. The microwave cloaks we've designed are about one wavelength thick, and they hide objects that are about 5 wavelengths in diameter. That's 5 microwave wavelengths. But if we were to hide the same object for visible light, that would be more like 500,000 wavelengths. In other words, we need to scale down the feature size in our cloak in order for it to work at visible wavelengths. But at the same time, we need a gigantic number of those features. And the features I'm talking about are as simple as voids, but nevertheless, it's not that easy to make tiny voids with the dimensions of order 100 nanometers and have millions of those features in the device. So it is possible. There are actually technologies out there that in reasonable time can fabricate structures out of polymers with feature sizes down small as 100 nanometers. One such process is called two-photon polymerization stereolithography. And if you look it up on the web, you'll find some beautiful images of microscopic objects with extremely fine resolution that are built that way from plastics. But you can imagine that making structures using nanotechnologies that span many decimeters or even meters is very expensive. So there's a challenge there in achieving this on a large scale and still keeping it fast and inexpensive.
Trying to find the invisible inside the prism. I'm Andrew Hiller for The Voice of Russia, and I've been speaking with Yaroslav Urzhumov. He's an assistant research professor and the technical coordinator of the Center for Metamaterials and Integrated Plasmonics at Duke University. Thank you for taking us inside this world.
Thank you very much.